Hey all, today we are working on related rates, section 5.6 in our book. So related rates, we're going to talk about related rates equations and strategy to solving it, and so simulated related motion. So finding related rates, assume that the radius r of a sphere is a differentiable function of t. Let V be the volume of the sphere. Find an equation that relates dV dt and dr dt. So I'm going to give myself a little bit more space in here because I know I write big. First thing I want to do is I need to color. All right, so we have a volume formula for a sphere, looks like this. 4/3 pi r cubed. We are finding the derivative with respect to time. So we are finding dV dt. How fast is the volume changing with respect to time? Sorry. So I have 4/3 here. I have pi. These are both constants. I leave it there. The next one, r cubed, I bring the 3 down, subtract 1 from r, and then I multiply also by the derivative of r. And then I'm going to simplify so that 4/3 r squared in there can be simplified. So I have dV dt equals 4 pi r squared dr dt. So we can figure that out. Next problem down here, assume that the radius r and height h of a cone are differentiable functions of t, and let V be the volume of a cone. Find an equation that relates dV dt, dr dt, and dh dt. So we need to write down, oops, I just pushed the button, not good. All right, there we go. 1/3 pi r squared h. So basically, it's the volume of a cylinder times 1/3. So we are finding derivative of V with respect to time. So I'm going to have that 1/3 pi. Those are constants. I'm going to bring the 2 down. I'm going to leave h because I'm not finding the derivative of h yet because I have to use product rule. And then I have 1/3. I got pi. I'm not sure why I don't know where I'm writing here. R squared. Oopsie. And dh dt. I'm supposed to have a little cursor when I'm writing. All right. So go down a little bit more. So we're here. Oh, there it is. All right, so we have dV dt. I'm going to simplify that whole mess up there. So I have 2/3 pi RH dr dt plus 1/3 pi r squared dh dt. So chances are you would probably have either the radius or the height there. It's going to be really hard to determine any one of these when you're missing 2 of the other ones. Okay, so strategies for solving related rates problems. So understand the problem, read through the problem, make sure that you know what you're solving for. Develop a mathematical model, draw yourself pictures. I draw pictures all the time. Label that parts that are important. Sometimes they give you extraneous information that you don't need. Be sure to distinguish constant quantities from variables that change over time. Only constant quantities can be assigned numerical values at the start. Other than that, I usually wait to fill values in at the very, very end. Write an equation relating the variable whose rate of change you seek with the variables whose rate of change you know. Differentiate both sides of the equation implicitly with respect to time, which we've already done, implicit differentiation. Substitute values for any quantities that depend on time. Note it is only safe to do this after the differentiation step. Substituting too soon freezes the picture, so it won't let it change if you're substituting a constant value in there. And finally, interpret the solution. So if you needed any of these, pause it, go back. There it is. So a police cruiser approaching a right-angled intersection from the north is chasing a speeding car that has turned the corner and is now moving straight east. When the cruiser is 0.8 miles north of the intersection and the car is 0.6 miles to the east, the police determine with radar that the distance between them and the car is increasing at 15 miles an hour. If the cruiser is moving at 60 miles an hour, the instant of measurement, what is the speed of the car? So we have all this fun information. I am going to draw us pictures. So the police cruiser is going this way, and the car is going this way. And we want to find this distance, right? What's the rate of change of the distance here? So I have all of that. And come on, color. Why isn't it liking me today? There we go. I'm going to call this X. And we do know rate of change of X, which is dxdt. We're going to just put these in. So this is the bad guy, right? Cruiser intersection. So this is going to be eventually when we plug all that stuff in, we're going to put that in, and we don't know this. We want to know how fast this guy's going. I'm going to call this Y, because Y goes up and down. The police cruiser is 0.8 miles. We know that the police cruiser is going 60 miles an hour, PH. I'm going to call this Z because we already have X and Y, so why not call that Z? We don't know Z right now, but we do know dz dt, and the rate of change between them is 15 miles an hour. I did mess up on one thing. I'm hoping maybe some of you noticed. This should be a negative 60 because we're getting closer to that. So this distance here is becoming negative. This distance here is becoming greater and greater and greater. We also can determine what our Z value is because these guys are related. They're in a right triangle. You can use the Pythagorean theorem. And you should get Z to be 1 mile. Ideally, I'm hoping you guys recognize the 3, 4, 5 most common Pythagorean triple. I do bring this up in class, but I wanted to say it again. Pythagorean triples also, you can double them and triple them and whatever, and you still have the same Pythagorean triple. So 0.6, 0.8, and 1 is, again, another Pythagorean triple. That's how I can do it so fast. So we're letting X be the distance of the speeding car, Y is the distance of the police car from the intersection, and Z is the distance between the two cars. We know these values, so I did fill it in on my picture, and then use the Pythagorean theorem to find dx dt. So we're finding the derivative. So I found it, well, they found it here, and then fill in all the stuff that we know. We know everything but dx dt. How fast is that speeding car traveling? Go through and find the value, and then you should get 105 miles per hour. Last but not least, we have a hot air balloon, and it's rising straight up from a level field, tracked by a field range finder. This is 500 feet. and I usually like to call this X, from liftoff point. At the moment, the rangefinder's angle, so we're looking at an angle here. Oops, that's supposed to be theta, is pi over 4. The angle is increasing. Oh, so we have d theta dt at 0.14 radians per minute. How fast is the balloon raising? So I'm going to call this y. And we are looking for dy dt. We know this, by the way, if you need it, is not changing. 0, what is it? Feet? Yep, feet per minute. This is radians per minute. I just ran out of space. So how are these related? Well, I have the opposite over adjacent. So that is my tangent. I keep hitting that button, I'm sorry. So tangent of theta, I'm going to start with the original, is y over x. And I have tangent of pi over 4. Why am I doing this? Because I don't know why. So this is 50. So I'm taking tangent of pi over 4, which is 1, multiplied by 50. So when x is 50, oops, that's 500. Oops. Y is, I really can't see where I'm writing. It's just all a guess. So y is 500. Then I need to go back. So there's my cursor. I need to find the derivative of that tangent function. So secant squared theta times d theta dt, nice, equals low d high minus high d low all over low squared. Okay, so secant of pi over 4, secant squared of pi over 4. So taking this whole thing, again, just a guess for me where I'm writing, equals, we know x is 500 and dy dt is how fast, that's what we're looking for. Where is my cursor? There, we don't know. Subtract y, which is 500, times dx dt, which is not changing. And then on the bottom, we have 500 squared. So now we're going to have to do, I'm sorry, that's so messy. I maybe could have written with the, oh, there's my cursor. Cursor showed up. All right, so secant of pi over 4 is what, 2 over square root of 2? Squared. I don't know, my cursor disappeared again. Okay, so I have 500 minus d, or times, that's a times, big times sign right here. Sorry about that. All over 2,500. Scroll down again. So I'm taking trusty calculator here, and I have 2 divided by square root of 2 squared, and I'm multiplying 0.14. So this whole thing on this side equals 0.28. Oh, this is starting to get really annoying. And all over 2,500, I'm gonna just quick do this on my calculator. So 0.28 times 2,500 divided by 500. I don't know why I didn't reduce. I get 1.4. So dy dt equals 1.4 feet per minute. And there it is.